Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important class of organometallic compound in the last few lectures, and these are transition metal carbonyl complexes. And these transition metal carbonyl complexes are important intermediates in many catalytic reactions, and that is why they are very interesting, as well as by the fact that these transition metal carbonyl complexes are one of the earlier organometallic complexes that have been synthesized, whereas their bonding properties, particularly the molecular orbital diagrams involving how they bond with transition metals, they are only recently developed. So, we have this we had this compound for a very long period of time, over a century, but understanding their bonding only happened maybe few decades back. So, from that perspective, these are a very interesting class of compounds. We have looked at the bonding we have looked at the bonding properties of this kind of transition metal compounds, the way they bond in a terminal fashion to the metal, or that they bridge, and the kind of bridgings that they may undergo. All of these were discussed in the last few lectures, including the last one also included the reactivity studies of these transition metal carbonyl complexes. And what we had seen is that these transition metal carbonyl complexes, which are of having 18 valence electron, underwent a dissociative mechanism, underwent substitution by whereas what we had also seen, that transition metal complexes which are 17 valence electron underwent substitution by an associative mechanism. And what we had also seen in the last class is that the rate of substitution for the transition metal 17 electron complex is significantly higher or significantly faster than the transition metal carbonyl complexes having 18 valence electrons. And this probably is because of the fact that the 17 valence electron species underwent association of a ligand reaching a 19 valence electron species, which is highly unstable, undergoing the substitution and giving back the substituted 17 valence electron species. So, because of this, in the last lecture we had seen that the substitution reaction was faster for case of 17 valence electron transition metal carbonyl compounds than that for 18 valence electron transition metal carbonyl compound. Now, with that in background, we are going to discuss another interesting type of reaction for transition metal carbonyl complexes, and these are addition reaction at the carbonyl, and this particularly relates to addition of nucleophiles to CO. So, for tungsten hexacarbonyl, in presence of lithium alkyl in diethyl ether, this R attacks the carbon of a coordinated CO, giving rise to the carbene complex, the way it is shown. So, this nucleophilic attack gives to a carbene complex. Now, we have discussed these synthesis in details, particularly with regard to formation of Fischer carbene complexes few lectures back, where exactly by following this procedure Fischer synthesized the first Fischer carbene complex, where the nucleophilic attack of R minus onto a coordinated CO occurred. Subsequently, alkylation by CH3 whole 3O BF4 gives the following carbene complex. And these are this famous Fischer carbene compound made way back in 1964, and the nucleophilic attack is favored as the carbon in coordinated CO possess larger positive charge than free CO, making the nucleophilic attack favorable. So, because of this carbon monoxide getting coordinated to the tungsten, there is a positive charge at the carbon carbon, and that favors this attack of the nucleophile onto this carbon. So, this is a very well known method of nucleophilic addition to coordinated CO, and was first successfully used for producing Fischer carbene complexes from transition metal carbonyl compounds, and we had discussed this while discussing the Fischer carbene or transition metal carbene complexes few lectures back. Similarly, formyl complexes can also be formed when the reaction of FeCO5 plus sodium plus MEO3BH minus. So, there is this hydride goes and attacks. So, the nucleophile over region H minus gives minus MEO3B, the boron reagent, leading to the formation of the formyl complex. So, nucleophilic addition of H minus to CO leads to formyl complex, as is shown over here. Now, in terms of the reactivity, we had discussed about substitution reactions in the last class, and also then about these nucleophilic addition reactions, that is addition of nucleophiles, which can be a carbon based nucleophile or a hydrogen based nucleophile onto the coordinated carbonyl carbon. And now we are going to discuss another interesting reactions, which are disproportionation reactions of transition metal carbonyl complexes. For example, 3 Mn2 CO10 plus 12 pyridine at 120 degree centigrade results in loss of 10 COs to give Mn Py whole 6 2 plus. So, here the manganese has been oxidized to plus 2 plus 4 Mn CO5 minus, where the oxidation state of manganese is minus 1. So, 0 oxygen state in the starting material, manganese 0 going to plus 2 and minus 1. And this is an example of disproportionation reactions of transition metal carbonyl complexation. This also is an interesting reaction which transition metal carbonyl compounds show that the metal in the 0 valence state of metal transition metal carbonyl undergoes disproportionation to produce manganese in plus 2 as well as manganese in minus 1 oxidation states. Now, with that we are going to discuss another variety of transition metal carbonyl complexes, and these are called carbonyl metallates. Or carbonyl anile. And these metallates are usually formed from the reaction of strong base with metal carbonyls. For example, the OH attack carbonyl carbon to give an addition product that decomposes to carbonyl metallates. The example of this type of reaction is given reaction of FeCO5 plus 3 NaOH gives Na plus H Fe CO4 minus plus Na2 CO3 plus H2O, and the reaction proceeds by this hydroxide attacking the carbon atom of the CO moiety, giving this so CO4 Fe CO2H, which in presence of 2 hydroxide H CO3 minus to give this sodium hydride FeCO4 complex as shown. So, the attack of nucleophile like sodium hydroxide on attack of sodium hydroxide on iron carbonyl complexes leads to the formation of metallate. So, this reaction is similar to what we had seen for nucleophilic addition reaction, and here sodium hydroxide attacks the carbonyl carbon, leading to these carbonyl metallate complexes. So, there are several methods of forming these carbonyl metallate complexes. The first one we had already seen is about the attack of hydroxide anion to FeCO5. The same can be done on Fe2CO9, and we will see how the reaction proceeds. Formation of carbonyl metallates, and we are going to see that several methods inclusive of the hydroxide attack leading to the formation of carbonyl metallates. For example, Fe2CO9 plus 4 OH minus giving Fe2CO8 2 minus plus CO3 2 minus plus 2H2O. Likewise, 3 FeCO5 plus triethylamine in H2O giving Et3NH plus H FeCO11 minus. To note here is that there is triethylamine and water. In presence of this base, hydroxide nucleophile would be generated, and that would undergo attack at the iron carbonyl, resulting in the formation of the metallate. One can have hydride as a nucleophilic source. An example of that is CrCO6 plus BH4 minus giving HCr2CO10 minus. So, here the nucleophile is H minus from BH4 attacking the CO. So, what we see that there are various ways of preparing these carbonyl metallates, and these are mainly low valent transition metal carbonyl complexes where the metal center is highly electron rich. Now, with that we are going to sort of move on to a new topic which we are going to be discussing in more detail in the subsequent topic, and this is about carbonyl metal hydrides. An important class of transition metal compounds or related analog of transition metal carbonyl compounds, where you have a carbonyl moiety and transition metal, and along with that there is hydrogen also acting as a co-ligand to transition metal. So, usually these transition metal hydride complexes are obtained by protonation reaction of metal carbonyls. The protonation of metal carbonyls leads to carbonyl metal hydride reagents. So, the protic compounds can affect the oxidation. Can affect oxidation with regeneration of neutral metal carbonyls. A very good example is given by this reaction, where carbonate metallate VCO6 minus when treated with acid H plus gives VCO6 plus half H2. So, these compounds can affect oxidation with the regeneration of the metal carbonyl complexes. So, there are several methods for preparing these carbonyl metal hydrides, and the first one is the reduction of CO2 CO8 plus Na, giving 2 Na plus CO4 minus, and that when protonated gives 2 HCO4. So, this is cobalt hydride tetracarbonyl, an important intermediate in hydroformylation reaction. Similarly, FeCO5 plus I2 gives FeCO4 I2, which when reduced with NaBH4 in THF gives H2 FeCO4. Reduction can also be done with molecular hydrogen. The example is given here. Mn2CO10 plus H2 at 150 degree centigrade and 200 bar give HMnCO5. So, with that I would like to conclude today's lecture, which we have started with the reactivity of transition metal carbonyl complexes. In this regard, we have looked at a very important reactions of transition metal carbonyl complexes, which are nucleophilic addition reactions on CO. And in this class, we have read about Fischer carbene complex, which was synthesized by addition of a lithium alkyl reagent onto a coordinated CO. We have also looked at the different carbonyl metallates of these transition metal carbon complexes, and what we had seen is that these are prepared a reaction similar to the addition of the nucleophilic reagents onto the metal coordinated carbon monoxide. We have looked into various preparative methods available for producing these metallate complexes, and after that we have looked into this new set of complexes, which are transitional metal carbonyl hydrides, particularly with respect to various synthetic procedures that are available for preparing these transitional metal hydride complexes. So, with this I thank you for listening to this lecture, and look forward to being with you in the next lecture, when we are going to discuss transition metal hydride chemistry in bit more detail, as we have just started the topic in the towards the end of this lecture. So, till then, goodbye and thank you.